and routes it to those events. There are three types of PubSub infrastructures. There are topic-based, where the matching and routing is done on the subject or the topic of the event. Then there are type-based, where all the event types are organized in a hierarchy, and you can use some hierarchical rules to do the matching and routing. And there are content-based, where the matching and routing is done on the entire contents of the messages. Clearly, content-based is the most general, and that has been the focus of our work. So what is the confidentiality problem here that we worked on? So the idea is that you want to deliver information that has been published by the publishers only to authorized subscribers and to nobody else. And you want to do it in a way where the publisher and subscriber do not trust a broker network. By that I mean, if you look at it, suppose as a publisher I trust a broker network, then I don't need to bother with extensive cryptography. I can simply give the message to the broker network, and the broker network will deliver to the subscribers. But that's not a very realistic assumption, because in an internet scale publish-subscribe infrastructure, the broker network will comprise peer systems, and it's very difficult to assume that the entire network of peer systems is secure and can be trusted. Second, and a closely related problem, is usage-based accounting, which also motivates the need for confidentiality. Now, the publisher publishes stock quotes, but wants to charge subscribers for the quotes that they have actually received. How do they do that? It's not an easy problem to solve. So we solve these two problems in a strong adversarial model setting using proxy encryption. That is, the publisher and subscribers don't trust the broker network. That implies that an adversary can read all the network traffic that traverses the PubSub infrastructure. The adversary will attempt to violate the confidentiality of the messages by reading them, and possibly modifying the integrity and authentication by trying to insert fake events or modify existing events in the network. Another strong point of our solution is that no modifications are needed to existing matching and routing algorithms. So here the problem is kind of easy to see. If you don't trust the publish-subscribe network, you cannot let brokers have access to the events. But it is precisely on the contents of these events that the brokers do matching and routing. So how do you solve the problem? One approach is to perform computations on encrypted data. So you encrypt the data from the publishers, and then the brokers would do all their matching and routing on the encrypted data using special functions. Now, these functions have been designed in theory, but they're very difficult to implement in practice. Furthermore, they also require modifications to existing matching and routing techniques. So our approach to this problem is based on the observation that only selected parts of an event's content need to be confidential, and matching and routing can be done without these sensitive parts. So what do? We encode the events in XML documents, and we selectively encrypt sensitive parts of the events. To do so, we use Bertino and Ferrari's XML document dissemination techniques. The next problem is now to distribute these keys to authorized subscribers. For that, we use Jacobson's proxy encryption techniques. So let's see how that's done. So first I said, let's give me an example of what we mean that you can actually encrypt only sensitive parts of contents. So the first example here is our stock quote dissemination service, and it's a stock quote price. And the publisher decides that this can be commonly agreed upon, that the only sensitive part is the current price of the stock quote. So you encrypt the stock price with a symmetry key K, and you leave the remaining part of the event contents in the open. And you allow matching and routings on other fields such as the volume, the name of the stock, the opening price, etc. The example below is a game score ticker, where in a similar way you can encrypt just the current score and leave the other parts unencrypted. Now, you have the sensitive parts encrypted with a symmetry key K. The challenge is, how do you get this key to authorized subscribers? If the publisher and subscribers could talk to each other directly, then the publishers would simply encrypt it with the subscriber's public key. But that goes against the philosophy of publish-subscribe, where you don't want the publisher and subscribers talking to each other directly. So the way we solve this problem is using a proxy service. So the publishers will encrypt the symmetry key K with the public key of the proxy service. Public key of the proxy service is PKPS, for which the decryption key is stored in a threshold manner in a set of servers at the proxy service. So here's how this happens, how this works. So the publishers publish the event where the selective parts of the event have been encrypted. The border brokers do the matching and routing on the clear text contents. The events reach a border broker that has a subscriber with interests in those events. The border broker then requests a transformation of the event with the subscriber's public key to the PSAS, the proxy service. The request is picked up by a set of coordinators that verify the request and sign the specific transformation task. That is, the transformation of the symmetry key K from the proxy's public key into the receiver's public key. And then we run Jacobson's proxy encryption technique, which is a threshold decryption and re-encryption algorithm on these servers to generate the result. Here's another view of the same process. What that does is, essentially the servers simply decrypt the key with their decryption key and re-encrypt it with the subscriber's public key. But this happens over a set of servers so that the plain text is never recreated in any single place. Furthermore, at the end of the transformation, the PSAS also generates a verifiable certificate of the transformation. By verifiable, it means that it's a publicly verifiable certificate that would allow any third party to verify that this key was actually transformed between this key and between this public key and the other public key. Yes?
But in a public subscriber, just we have a publisher, subscriber, and the broker network.
Yes.
Where does the PSAS fall in this?
Yes.
It's a new entity, right?
It's a new entity. So, so the first thing that happens is if you introduce a new entity, your question comes, it's centralized, potentially. That's not a good thing. And second is also performance issues. So yes, we are introducing new entity, and I'll talk about that in the next slide. So this verifiable certificate is what allows the publishers to provide usage-based accounting, because now it is a proof that you can charge the publishers, you can charge the subscriber based on what they have used. So now, as was just pointed out, if you have a single PSAS service for an internet scale publish subscribe system, you raise issues of centralization as well as performance. So we've done some scalability studies on this system, and we work backwards. So we need the transformation every time you deliver an event to a subscriber. So working backwards, we looked at what are per subscriber event delivery rates that you typically need. So we said that if you want a frequent delivery of events, every subscriber will receive an event every minute. More reasonable is something like an event every 20 minutes. And then we looked at the architecture, and it turns out that, like most public key systems, the performance bottleneck is the exponentiation. So we looked at performance exponentiation measurements on common desktop and server systems, and for a reasonable price desktop, we get a range over here. So our scheme, depending on the frequency with which you want to deliver events, delivers somewhere between 20,000 and 50,000 subscribers per PSAS using current technologies, which is reasonable for many applications, but maybe not enough. Then the issue comes of centralization, where you can actually replicate the PSAS and have solve the availability problem that way. And furthermore, by replicating, you also increase the scalability of the system. And the scalability increases approximately linearly. So if you have 3 PSASs, you triple the overall service rate that you can provide. So the cost is high, and they need to do more work to see if there are ways in which we can reduce the cost or provide other techniques. But this is a solution to this problem, which has been a hard problem to solve and was proposed about 2 years ago. And to our knowledge, no other solution has yet been proposed. Now, moving to the third messaging infrastructure, namely group communication. So secure group communication is needed to support many military and commercial applications. For example, conferencing, command and control systems, and interactive distance learning. Here, the need for confidentiality has been clearly stated by many research groups. And what you need is a group key management solution. So the way they solve the confidentiality problem is they give